Okay, we're back for more here. We started out with the last video. We've actually gotten into true geometric dimensioning and tolerancing. We're working our way through the different controls in the group of form controls, and we talked about straightness, which is ultimately a pretty straightforward concept. Once you realize that you have to have a basis of straightness that is absolute, and that is the geometric line. And then it's just a question of which lines on what aspect of a part or a feature are we going to try to control. And we saw already that we can sort of diverge into some aspects of geometry that you probably haven't thought about. And the important concepts that we carried away from those first couple of videos were that there are really two fundamental types of elements that we can control for straightness. There are the surface elements, and on even something as simple as a shaft, the outer surface elements that make up the OD of the part. There is an infinity of those elements. And each one of them can be controlled independently, measured independently. Obviously, with an infinity, you have to sort of draw the line and pick out the most important, or pick a number and check it. But that's a very important distinction. We're going to see that distinction between surface elements and derived elements later on in other controls. And the real important thing to carry away from this is that when you make that distinction between a surface element and a derived median element, it often, almost always, has an impact on the nature of the tolerance zone. Is the tolerance zone, in the case of surface elements, it was two parallel lines that start where the feature starts, ends where the feature ends, and they're spaced whatever the tolerance size is noted in the feature control frame. With the derived median element, we saw that we went from an infinity of these lines to a single line that is really actually a conceptual feature. It usually doesn't exist, or it certainly isn't accessible. The center line of a solid bar material isn't accessible. The center line of a tube is purely conceptual. There's no there. There's nothing but air. So we actually have to derive both of those elements mathematically, and that's why it is called a derived median element, and normal people would call it a center line. You're going to see later on that we can also have derived elements that aren't linear. We can have derived planes are certainly common. So keep this distinction in mind of surface elements and derived median elements, and how you can tell whether you're controlling one or the other. Again, it is not as clear as it should be in Y14.5. You've got to look carefully at the feature control frame, where it is placed, and what information is inside of it. And if you review the video, that should refresh your memory about that. The other very, very important concept that we came across was the idea of a material modifier, a material condition modifier, either an M in a circle or an L in a circle, that actually changes the size of the tolerance zone in a predictable fashion based on how much material is in that feature. We also introduced the concept of a male and a female feature so that we can get the limits established correctly, and I showed you how to establish those limits. Once you take the dimension, you establish the upper and the lower limit, you decide whether it's a male or a female feature, and then you mark it according to whether it's the maximum material condition limit or the least material condition limit. Probably the hardest part of all of that is to read a feature control frame that uses those modifiers. It can get a little bit confusing. So far, we've only seen the material condition modifier used in the tolerance zone block information. Later on, when we get to using those additional little square blocks that go on the back end of the feature control frame, which are datum blocks, we're going to actually see that material condition modifier used there also, or potentially used there. But right now we're working strictly with the very simple form version of the feature control frame, just a symbol and a tolerance zone block information. And if you remember, when we said that we want to be able to look at this very compact symbolic statement of requirement and be able to turn it into English. And the way I would do that is say, I have a straightness control with a 10 thousandths diametral tolerance zone, but that tolerance zone is 10 thousandths only when the feature is at maximum material condition. In other words, when the shaft is at its largest, I get a 10 thousandths tolerance zone. As I get smaller and smaller from one part to the next, as that diameter goes down from maximum material condition, I get to add on a thousandth for thousandth basis additional size to this. So this 10 thousandths only applies at maximum material condition. And that's the way you always interpret the material condition modifier in the feature control frame. Okay, that is sort of form controls in their essence. Now again, we can get fancy with some of these controls. I'm always leery of doing that because it always is a source of a problem either by the engineer who puts the requirement on the drawing or the person who has to read it, the machinist or the inspector. So once we get past these very simple feature control frames, you want to be careful about how you use them. If you look in the handout, in the tolerances of form handout that I put on Canvas, you'll see that in figure 5.4, we have that situation. Okay, this form where you have the tolerance information stacked up one on top of the other is used in several ways in GD&T. This is a composite control, and it's meant to prevent that tolerance being applied all in one place. So that, well, I'll show you what it would look like if it were. Okay, bear in mind again that these examples are meant to be metric. So in this instance, we have a long shaft that was 100 millimeters long. That 100 millimeters is roughly 4 inches, so it's not the super long, but when we look at this composite control, we always sort of read them just like we would read a book. We read the tolerance zone the tolerance information from the top down. So we read this one first, and that says that regardless of feature size, since there is no material condition modifier here, you can sort of imagine that imaginary S is there. So that means that I have a diametral tolerance zone of 0.4. I know this is a derived median element because the feature control frame is attached to the dimension of size. The tolerance zone then is a cylinder that is 0.4 400 thousandths in diameter. Okay, so, and we could leave it at that if we wanted to, but if the engineer is concerned that that fairly large tolerance might be used or may result in a condition that he really doesn't want. And what he's probably most concerned about here is once you have established that tolerance zone, once you have that at 0.4 diametral tolerance zone, that derived median element, that center line, can do anything it wants within that space. So again, the center line could do this, still an acceptable part. So if the shaft were all wavy, as long as it doesn't exceed that 400 thousandths, that's an acceptable part. What he's probably more concerned about is that center line takes something like that, a hink in the straightness, all in one place, and it's, you know, basically a bent shaft. So he has added basically a modifier to the tolerance zone and saying that yes, you can have a total of 400 thousandths tolerance zone over the length of the shaft, but in any given 10 thousandths, of space along this length, I'm sorry, 0.1. So in any given 100 thousandths over the length of this, in any given 25 millimeters, so any given 25 millimeters over this 100 millimeters length, the total amount of unstraightness or lack of straightness can only be 0.1. So he's basically said that the total amount of tolerance over the entire length is 400 thousandths, but in any given inch, any given 25 millimeters, there can only be a quarter of that. So in that larger tolerance zone, we have sort of a nested or embedded smaller tolerance zone that's a quarter of the size. And what that effectively does then is says that yes, you can have all that tolerance, but it has to be distributed somewhat evenly over the length of the part. Now again, you can do something like that. I don't know that I've ever seen anything like that done. But the tool is there to do it, and the tool and the definition I want you to remember is the composite control. Okay, now finally for straightness, I'm going to just show you another one that's something that you can do. Geometrically it makes sense. In reality, I don't know that I would ever do what they're suggesting here, but I'll explain it, and you'll at least get the mental picture of why you can do it using the straightness call-out. Okay, so here is something that is possible because of the nature of what we're controlling here. We are controlling linear elements. First thing we're going to ask ourselves, are we controlling linear elements on the surface or some sort of derived element? Since the feature control frame is pointing right to these surfaces, the top of this block, we know that we're controlling the surface elements. In other words, there's an infinity of lines along this surface, along the top of this block that we can control, and each one of them has a control as noted on the drawing. What's going on here though is kind of interesting, and again is a consequence of the fact that we are controlling a planar surface by individual lines. If you look at the left side view here, you'll see that there's a tolerance zone of 50 thousandths on this surface and 100 thousandths on this surface. Well, in reality, that's all one surface. That is one flat face of that block. So how can we have two different tolerances on there? Because we are controlling them as linear elements. So if you visualize this as a surface, sort of as a isometric view, the 50 thousandths requirement applies to the lines that are running in that direction. The 100 thousandths requirement applies to lines that are running in this direction. So, if you picture that geometrically, you can sort of think of it as this book, and this page being a plane, a geometric plane. And what would happen if I had two different linear straightnesses on this part? Well, it would look something like this. So in this direction, I have very good straightness. Let me curl it up here a little bit better. I have good linear straightness here. Obviously in this direction, I don't have good linear straightness. So that's an instance where you would have two different controls for that surface. It's really a, I guess you would call it cupping or a curling control for that straightness. Okay, again, this is, I won't say it's completely out in the weeds, but it is something that I haven't encountered very much. I've seen straightness requirements a lot, but I haven't seen them used to control different aspects of a plane. So again, it's in the standard, but it isn't, I don't think, going to be very common. Okay, I think what I'm going to do here is I'm going to terminate the video at this point, then we'll kind of move on to flatness. Now, flatness versus straightness, again, this is in the realm of pure geometry, again, where straightness is a comparison to a geometric line. Flatness is going to be a comparison of a feature to a geometric plane. Again, flatness is a super critical requirement in all precision in measurement and machining. All these aspects rely on some flatness basis. Someone asked me, I think last time I taught this course in figure 5.4 or 5.6, could that surface have been controlled, or should it have been controlled with a flatness control? Yes, it probably could, or definitely could, and probably should have been. What they're showing is that you can, if for some reason you have a part that preferentially wants to curl in one direction, you can control it by a linear control, and as long as that's okay, then you have a control that isn't going to cause you a lot of problems. I guess a part like a rain gutter would have a control like that. It has to be straight in one direction, curled in the other. I don't know where you would use it, but anyway, that's the idea. And the flexibility of the system is the important part here, is that if you think through the geometry, you're pretty much going to have a tool and a method in GD&T to put a control on whatever is troubling you about that feature. Okay, again, I'll terminate here and then we'll move on in the next video to flatness.